Now, this is a problem where you have a compression station with multiple compression in series is to provide a gas discharge pressure of 1500 psi. Eh, The gas inlet pressure and temperatures are 100 psi A and 80 degrees Fahrenheit respectively. Now, it says how many compressors in series will be required if the discharge temperature is limited to 250 degrees Fahrenheit? The ratio of specific gravity is 1.4. Now let's begin. Now let's look at a compressor. Now you we also know that the ideal gas equation you have P1V1 divided by T1 is equal to what? P2V2 divided by T2. Now from this from this now we are considering a situation an adiabatic compression system. So you have P V raised to power the heat ratio is a constant. So that means that P one V one raised to power this is equal to P two V two raised to power. So that means it now implies that from this expression here now we're looking at one, two, and the third one. Now from this expression here we have P2 all over P1 equal to V1 all over V2 all raised to power. So now and this is equal to what? 1.4. So let's make use of the 1.4 here now. So we have P2 all over P1 equal to V1 all over V2 raised to power 1.4. So it now implies that V1 all over V2 is equal to, now if you multiply the powers by 1 all over 1.4, we multiply the power by 1 all over 1.4, you now have P2 all over P1 raised to power 1 all over 1.4. Because if you use 1.4 to, if you use 1, if you multiply this by 1 all over 1.4, you are left with this. So now you're multiplying both sides by both powers by 1 all over 1.4, you have this. So that means V1 all over V2 is equal to this. Now we can reverse this. So say V2 all over V1 is the same thing as saying P2 all over P1 raised to power minus 1 all multiplied by 1.4. So you have something like this. So now we can invariably write this to be V2 all over V1 equal to what? P2 all over P1 minus 1 all over 1.4. We also know that the ideal gas equation is P1V1 all over T1 equal to P2V2 all over T2. Now Now, if you rearrange this, you have T2 all over T1 equal to what? P2 V2 divided by P1 V1. So now we have P2 P1 times V2 V1. So that means T2 T1 will now be, now we have P2 all over P1. Now V2 all over V1, which is this. We put it here, you have P2 all over P1 raised to power minus 1 all over 1.4. So if we, since it, since you have P1 over P2 here, P1 over P2, they are the same, we add the powers. So we invariably have T2 all over T1 equal to P2 all over P1 raised to power 1 minus 1 over 1.4. So this will give us P2 all over P1 raised to power 0.4 all over 1.4. So we have gotten the ratio of the temperature. Now, the suction pressure, the inlet pressure is 100 psia at the temperature of 80 degrees Fahrenheit. Now, we were to get a delivery pressure of 1500 psia. Now, and we are not to exceed the temperature, it should be less than or equal to 250 degrees Fahrenheit from what was given. Now we are asked to calculate how many stages. Now, you know, the compression ratio of one, if the compressors are in series, the compression ratio of one compressor in series is equal to the overall compression ratio raised to power 1 all over the number of compressors in series. Now, first let's check if this one, let's check if it will give us a temperature higher than this. Now, let's look at it from this angle. Now, we have the T2 all over T1 equal to, now, the delivery pressure is 15,000 divided by the input pressure, which is 100 raised to power 0.4 divided by 1.4. So now, we say the temperature now will now be 15 raised to power 0.4 divided by 1.4 times this temperature, which is 80 plus 460. So this will give us what? This will give us So this one will give us 1170.6 degree Rankine. Now to change it to Fahrenheit to minus 460. So from minus 460 from that to give us 710 degree Fahrenheit. So this value is greater than 250. So it's not possible for one stage. So it's not possible for one stage. Now let's now look for how many stage compressor that can do this. How many stage compressor that we can use so to have a lesser delivery pressure, temperature, sorry. So now for us to do that, now we are looking at we now need to estimate kind of. We're able to do this. We're looking for R, where the overall compression ratio of the compressors in series raised to power 1 all over the number of compressors in series. So now the overall compression ratio is 15 now from our calculation, and this is equal to 15 raised to power 1 all over the number of compressor series, so which is equal to R. Now we also want a situation where R, which is a compression ratio raised to power 0.4 all over 1.4 equal to T2 all over T1, where we want T2 to be less than or equal to 250 degree Fahrenheit. Now let's look for the R that can give us that. So invariably this equation will now have to change to saying T2 all over T1 greater than or equal to R raised to power 0.4 divided by 1.4. So we're looking for the R that will give us this expression. Now we know T1, which is 80 plus 460. So this will give us 0. This is 540 Rankine. 540 Rankine. So now that is what we're going to put in here. So now we have T2 greater than or equal to 540 degree Rankine times R, we are looking for raised to power 0.4 divided by 1.4. So now, and then T2 is what? T2 should be less than or equal to 250 plus 460, which is what? 710-degree Rankine. Degree Rankine. So that means we're going to say 710 is greater than or equal to 540 times r raised to power 0.4 divided by 1.4. Now, if we divide both sides by 540, we have 710 divided by 540 greater than or equal to r raised to power 0.4 divided by 1.4. So now we can rearrange this to be r raised to power 0.4 divided by 1.4 less than or equal to 710 divided by 540. Now, let's multiply the powers of these two by 1.4 divided by 0.4. So this, you have 0.4 divided by 1.4. Multiply the powers by 1.4 divided by 0.4. Sorry, 710, 540. Multiply the powers by 1.4 divided by 0.4. So this will cancel out. You have this, the compression ratio now will now be 710 divided by 540 raised to power 1.4 divided by 0.4. So now the compression ratio should be less than or equal to 710 divided by 540 all raised to power 1.4 divided by 0.4. So let's look at this. So the compression ratio should be less than, let's work it out with a calculator. 710 divided by 4 divided by 540 raised to power 1.4 divided by 0.4. So R should be less than 2.60631. Should be less than, R should be less than this for us to have a delivery pressure of, sorry, a delivery, for us to have a temperature, a T2 less than or equal to 250 degree Fahrenheit. Now, let's now calculate for this. Now, let's assume this, so R is less than this. So now we have 15 raised to power 1 all over n equal to what, R. And R is less than or equal to 2.606, meaning 15 raised to power 1 all over n is equal to what? Is less than or equal to 2.606. Now, since we have gotten 15 raised to power 1 all over n is equal to 2.606. Now, let's say take log of both sides. You say log of 15 raised to power 1 all over n is equal to log of 2.606. Now, this expression here is written as 1 all over n log 15 equal to log 2.606. Now, I don't have to explain this, how I got this, because if you want to know how I got this, there are some things I solved on logarithm. You can go look at it and be able to understand why this is like this. So now, what I'm going to do now next is to divide both sides by log 15. So this will cancel out this. You have 1 all over n equal to log 2.606 divided by log 15. You know, this is less than, less than, less than, less than. Now, let's inverse this. So you now have n all over 1 equal to log. So this one will now be greater than 2.606. Will be greater than man. So if you reverse it, you have 15 log 15 all over log 2.606. So that means n is greater than, so let's say log 15 divided by log 2.606. So we have 2.827. So roughly n should be equal to 3. So it should be a 3-stage compressor. Now let's check. So if we say it's a 3-stage compressor, that is the least, because since n is greater than this, the smallest number of compressors 3 that we can use now. So now, if it's a 3-stage compressor, so now let's look at what is the compression ratio of each of those compressors in series. So each of those compressors in series will now be, the compression ratio will be 15 raised to power 1 all over 3. So 15 raised to power 1 all over 3, that is the cube root of 15. So 15 raised to power 1 divided by 3 give us what? So we have 2.466. So the compression ratio is 2.466. So now let's check. Now we know the temperature, the discharge temperature from each of the compressor from each of the compressor. Let's calculate it now. So we have the compression ratio to be 2.466 raised to power 0.4 divided by 1.4. So now you have T2, which will be equal to 2.466 raised to power 0.4 divided by 1.4 times the T1, which is 80 plus 460, will now be 540 times 2.466 raised to power 0.4 divided by 1.4. So Let's calculate this. So we'll say 540 times 2.466 raised to power 0.4 divided by 1.4 equal to, so we have 698.86 degree Rankine. Now, if you minus 460 degree Rankine, we'll have what? So minus 460, we have 238.9 degree Fahrenheit. So you see, 238.9 degree Fahrenheit is less than 250 degree Fahrenheit. So the least compression ratio, least number is 3. Sorry, is the least number of compressors that can be put in series. Identical compressors that were put in series to give you the output delivery pressure of 1500 psi is 3. From this our calculation is 3. So which will also give you a temperature that is below a delivery a discharge temperature that is manageable, which is 238.9 degree Fahrenheit, less than the 250 degree Fahrenheit limit. So this is the end of this exercise. Please do well to subscribe to my channel so that when you subscribe, you'll be the first to watch each of my videos. Thank you and God bless. Do have a nice day.